Today we'll start with a couple of linear algebra problems that are formulated very nicely, or actually solved very nicely, in tensor notation. The first one is the problem of quadratic form minimization. So in linear algebra notation, it's formulated the following way. Consider a function of x, where x comes from Rn, x1, x2, through xn. It's given by this expression, 1/2 x transpose ax minus x transpose b, where A is a square matrix. Our goal is to evaluate the gradient of f, which is all partial derivatives of f with respect to all the different x's. Does anybody know the answer?
Ax equals b.
Ax minus b, which is what you're trying to say. So the answer in the linear algebra terms will be that the gradient of f equals ax minus b. Is that true even when A is not symmetric? What if A is not symmetric? What's the answer then?
It's not.
What if A is not symmetric? All right, so that's one question to keep in mind. And the other is, how do you derive it? So this is an example where the formulation is perfect in matrix notation, and the eventual answer is perfect in the matrix notation. But the actual differentiation is very difficult to carry out in matrix notation, because the matrix notation does not give you access to the individual elements of the vector x and to the individual entries of the matrix. And that makes differentiation very difficult. I would actually say almost impossible, unless you do it by some other means. But this notation is not conducive to finding derivatives with respect to the components of x. But in the tensor notation, it's a breeze. So let's just do it sort of as a warm-up for today's very intense lecture in terms of indices. So this will be just our warm-up. And then we'll see what happens when A is not symmetric. Because it seems like not everybody knows, or not anybody. Is that fair to say not anybody knows the answer?
No one.
No one? All right. So here's the same thing in tensor notation. So I actually find this even more appealing written in tensor notation, because the order doesn't matter. Minus x transpose b, which is x I b I. So here it is. You might want to ask me, well, why does A get lower indices? Who says it's a tensor? Well, in this case, we can talk about the tensor properties of A, but that's not important here. The placement of the indices does not necessarily carry with it the concept of change under change of variables, because we're not going to be changing variables here. It's just this problem. And then we're about to evaluate the derivative. So what can I take a derivative with respect to? So what do I want to write? df dx what? Can I write df dxi? No, because it's already taken. J is already taken. Okay. So I have to write k. df dxk equals. And of course, I will use the product rule here and here. And I will have 1/2 a I j dxi dxk xj. You guys agree? This being the first step of the product rule, plus 1/2 a I j, leave xi alone, dxj dxk. Oh, I'm going to have just enough space. Minus dxi dxk bi. And at this point, I usually take a step back and make sure all the indices work quite nicely. K is the live index, I and J and I in this expression are contracted away. They're the dummy index. So everything's matching. So now let's really combine two steps into one. What is this symbol? No, it's not the Jacobian because we're not relating one variable to another. It's related, but it's different. It's all it's the derivative of all possible x's. Right, x's are only the independent variable here. So it's either dx1 dx1 or dx1 dx2 or dx1 dx3 and so forth. So this is something that never changes in tensor calculus. You always have to take a step back and sort of reinterpret the expression for yourself. So if the independent variables here were called not x1, x2, x3, but x, y, and z, this would be dx dx or dx dy or dx dz, which is 1 if they match and 0 if they don't. So all this is delta ik. And of course delta ik will just rename this I into k. So it becomes 1/2 a, well, we'll get to parentheses in the next step. So k, I is renamed into k. A, k, j. What did I say?
Yeah.
No, I have two lower j's. There you go. Sorry about that. Oh, much better. xj. xj. And tell me what the next term is. Plus 1/2 ai, so this will be delta jk. J will be renamed into k. So it's 1/2 a I k x I minus, somebody else tell me what's that term going to simplify to? ek. ek. Now I will do one instance of renaming. I will rename this I into j, answering everybody's question of can you rename indices in a single term? And the answer is yes. This is a sum of 3 terms, or n terms. I can encode it with I, or I can encode it with j. So I will switch from encoding it with I to encoding it with j. So it will be ajk. Is that the one I want to read? Yeah, I think so. Or let's rename j and stick with. So we have I. So, and that will result in 1/2 AKI plus AIK XI minus BK. And that's actually the final answer. Now, if A is symmetric, then these two terms are the same. Then AIK equals AKI. So I will just write it in the next line. If A is symmetric, then it's 1/2 A K I X I minus B K. And here you have it. It's the answer that you know. But if A is not symmetric, what would you call this in matrix terms? If this, let's say, if this is A, then what is this? A transpose. So the general answer is actually, if A is not symmetric, then the general answer is A transpose plus A. 1/2 A transpose plus A. It's called the symmetric part of A.
Wouldn't that make it symmetric? If you're adding the transpose to A?
That's right. So even if the matrix is not symmetric here,
You make
the gradient, no, you don't make it. The gradient ends up having a symmetric matrix in it. So if you think back to linear algebra, actually if you replace this A with 1/2 A plus A transpose, which is called the symmetric part of A. It'll change this matrix without changing the quadratic form. Because this matrix has, this product has A12 x1 x2 and A21 x1 x2. And if you factor out x1 x2 in parentheses, you'll have A12 plus A21. So it's really the only thing that matters for this in a product is this symmetric part. Yes.
Shouldn't there not be a 1/2 on the bottom line?
There should not be a 1/2. Thank you. That's right. So if A is symmetric, then these two are equal. The 2 cancels 1/2, and we have what's now interpreted as AX minus B if you were to go back to matrix notation. If A is not symmetric, then the answer is 1/2 A transpose plus A. So, perfect problem for tensor notation. And really woefully undertooled if you don't have the tensor notation and you're faced with this problem. Any questions? Yes?
Why is A not a function of X?
That's just in the product. You're right. You keep thinking back to the to the physical space. So this is just a small little application in linear algebra where A is known to be a constant.
Oh, okay.
If A is not, if given to be a constant, if A is not a constant, then this would not be its gradient.
Okay.
There would also be A prime in there somewhere. Sure. Okay, that's number 1.